Salutations everyone, Dustin here. This video is a continuation of a two-part series I am making. The previous one was about arithmetic sequence, series, and means. In this video, we'll be learning about geometric sequence, series, and means. So, let's solve for this one. Find the common ratio and eighth term of the geometric sequence 2, 6, 18, 54. So as you can see here, even without this geometric sequence word, we can immediately tell that this is a geometric sequence because the difference between 2 and 6 would be 4, but the difference of 18 and 6 would be 12. So it's not an arithmetic sequence. It moves by multiplication, not through addition. So first things first, we use the geometric sequence formula. So we have here geometric series is equivalent to a sub 1 times r raised to n minus 1. So in order to find the common ratio, we must take a specific term and the one before that. So let's take 6 and 2. So we take 6 divided by the term before that, which is 2, and we have 3. That will be our common ratio. Similar to 18 and 6. Sorry, this is just a line. It's not divide. So 18 and 6, when you divide it, you'll still be 3. So this is indeed our common ratio, 3. Our n would be the 8th, because it is the 8th term, and a sub 1 would be 2. So we'll just plug it in. 2 times common ratio is to n minus 1, or 7. But before you do some calculations, ensure that you actually calculate it right. Don't get lost in the PEMDAS dimension, because it won't be much great. You see, if you multiply 2 and 3 and raise it to 7, you'll end up with a totally different number. So what you'll do first is you multiply 3 times 3 7 times, or 3 raised to 7, then you multiply by 2. So it's basically just this, although it'll be a lot more messier if we add these parentheses. But yeah, just know that since there's an exponent here of 7, you use it first on the 3, then you multiply by 2. So using a calculator, you can see 3 raised to 7 would be 2187 times 2. And our geometric, the 8th term of our geometric sequence would be 4374. Quite large, yes indeed. So moving on. Write the first 5 terms, an explicit formula for a geometric sequence, with a sub 1 being 5 and the common ratio being 3. So it is actually quite easy. So it says that our first term here would be 5, and we will write the first 5 terms. We already have the first term, which is 5, so we need the 4 following ones, and for 3. So you can use the formula that we used prior. If we use this formula, let's solve for the second term. We would end up with 5, 3. 2 minus 1 would be 1. 3 raised to 1 would be 3 times 5 would be 15. But as you saw, it's somewhat tedious, especially that we need to calculate 4 terms. What if it asks us to calculate even more terms? It'll be rather tedious. So what we'll do is we just use basic logic in order to solve this much more quicker, especially for exams. It will be much easier, unless it tells you to explicitly write each and every formula. I just wrote this as reference, but if you're not told to really write every single one, you can just use this logic. So as you saw, our first term will be 5 multiplied by our common difference, which is 3. We can also just multiply by this 15 by 3, so we get 45. Oops. Anyways, fifth term would be 405. So the terms would be 5, 15, 45, 135, and 405. Moving on. Find the missing terms in the geometric sequence of 81, 27, and 9. And blank, and 1 over 3. As you can see here, we are decreasing in value. Unlike the other ones where we increased, in this sequence we actually reduce numbers. So we still use the original formula here. It's basically just repetitive, honestly. Once you really get a hang of these calculations, it would be just repetitive and just easy. Anyways, in order to find our common ratio here, again we put the second term over the first term, and simplifying this, we actually get 1/3. Quite simple. So put in here 1/3 and minus 1. So we'll be looking for, let's say, the fourth term. So 4 minus 1, or 3. So using exponent rules, 1/3 raised to 3 would simply be 1 over 27. We multiply 1 3 times, so we can have it like here, 1 3 3 3, or 1 over 27. So we have 81 times 1 over 27, or we get 3. So the answer here would be 3. Okay. Now again, we could use that formula all over again, or what we could do is actually see the pattern. 81 divided by 3 would be 27. 27 divided by 3 would be 9. 9 divided by 3 would be 3. And 3 divided by 3, yes, it would be 1. And 1 divided by 3 would be 1/3. So our answer would be, the missing terms are 3 and 1. Alright. So, what if it asks you to sum up them? So there are actually 2 types of geometric series. There are 2 types. There are finite geometric series and infinite geometric series. So a finite geometric series is basically just add terms from a sub 1 up to a sub 100. And let's just put finite. And an infinite would be something like a sub 1 up until infinity. The reason why we don't get finite and infinite arithmetic series is because an infinite arithmetic series is already infinity. However, in geometric series, our common ratio could be less than 1. And if it is less than 1, it actually converges. So let me show you an example. So let's say you get half piece of cake, and after that you get half of the half, or 1/4, another half of the half, which is 8, and so on. As you can see, when we add this up, let's just get the greatest common factor. 1/8, 8/2, and 8/4. If we try to sum them up, so we get 7/8, and as we go so on and so forth, we actually notice that we don't actually go to a huge large number. Rather, we actually end up with a specific value, or what we converge. We converge into a single value. And there might be questions out there that asks if a geometric series an infinite geometric series diverges or converges. In order to know this, just memorize this. Divergent convergent. Oops. So basically, based on their root words, divergent is to diverge or to separate, or it goes on to infinity. So like diverge, but converge, it ends up to a singular value, something like that. Just a visual representation. Anyways, you'll know if it is a divergent, if it diverges, if your R, if the R's value, if it's absolute value, if it's the R or the common ratio's absolute value is equal to or greater than 1, and a convergent one is less than 1. Practically speaking, you can actually somewhat understand it from the forms itself, because as you can see here, if your multiplier would be 1 or greater than 1, well, obviously you'll go to infinity. Let's say something like 2 times 3 plus 2 times 4, and so on. It'll be astronomical. If you add them all up, it'll be extremely large. However, if your common ratio is less than 1, let's say 2 and 0.5 plus 2 0.25, it actually decreases in value. So eventually down the line, it will converge into a singular value, meaning it won't end up to infinity. So let us set an example. So first, we would be using the formula for a finite geometric series. It would be equal to E sub 1 times 1 minus R minus r raised to n. So let's just plug in the values. So our first digit being 2, so our first term would be 2 times 1 minus r until the fifth term. So our r would be 3, n will be the fifth term, 1 minus 3. Now again, be careful with PEMDAS. You want to use this exponent first before you actually do 1 minus 3. So 3 raised to 5 would be 243. 1 minus 243 would be negative 242. Over 1 minus 3, or 2, multiplied by 2. It's negative 2 actually. So once we calculate this, these negatives will cancel out, and so are these two ones. So we end up with a value of 242. Moving on, the sum of the first 7 terms of the geometric sequence. We would be using that formula again. So first term, or 7, over 1 minus r, which would be 8 over 4, or 2. 2. So our n would be 7. So plugging in a calculator, 2 raised to 7 would be 128. So 1 minus 128 would be negative 127 times over negative 1. Negatives will cancel out. Just multiply 7 with 127, and we end up, so we use the formula again, a sub 1 over 1 minus r raised to n. Our first term would be 7. Sorry, it would be 4, not 7 actually. We have 7 terms, but the first in our sequence would be 4. Multiplied by 1 minus r raised to n. So our r would be 8 over 4, 2. So 1 minus 2, and our n is 7, not 4, 7. So 1 minus 2. So plugging in the calculator, 2 raised to 7 would be 128. Get negative 127 over negative 1. The negatives cancel out. 4 times 127 would be 508. Moving on. Now here we have it. The one that I mentioned earlier. Determine whether 1 plus 1 half plus 1 4 plus 1 8 converges or diverges. We use the formula a sub 1 over 1 minus r. Quite similar actually to the finite series, except you don't have n because, no, it's infinity. So yeah. So when we plug in the values, our first term would be 1 minus, so 1 minus 1 half, so our common ratio would be 1 half. So we would get something like this. So 1/1/2. So you might be confused, like, okay, how do we do this? We divide a divide. So one thing I could do is express, since the denominator is already expressed as a fraction, we express the numerator as a fraction as well. So I have 1/1 over 1/2. So again, put it here and here, or we get 1, 2. Multiply it, we get 2. Interesting. So as you can see here, our r is 1/2, and clearly 1/2 is less than 1, meaning it converges into a value, and that value would be 2. So it says that if you continue this, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, and so on and so forth, we end up with 2. We don't end up with infinity, we end up with 2. So let's see more. Let's see if we could find one that diverges. So here we have it. Oops, why are there 2? Okay, just don't mind that. Don't mind that. Okay. So determine whether 3 plus 9/2 plus 27/4 plus 81/8 converges and diverges, and find the sum if it converges. Alright. So we use the formula again. A sub 1 or 3 and 1 minus r. So be 9/2 over, let's just use it as fraction, 3/1, 3, 1, 9/6, or 3/2. So our common ratio would be 3/2. And clearly 3/2 is greater than 1. But you might say, well, okay, you claim it is divergent, but can you prove it? Okay, so as you can see, our common ratio would be 3/2. If we calculate this, and we get -6. However, this is invalid because when we do, the series actually grows and grows. So let's actually just convert this 3/2 into 1.5. Let's plug it in 3. So 4.5. 4.5 times 1.5 would be 6.75, so on, 12.125. And if you add all of these up and even continue, you'll end up with an enormous number. So it actually grows towards infinity. And when that happens, it is divergent. Because if you just keep on going on and on, it just goes to infinity. It'll be extremely large, and therefore it is divergent. And we can't sum it because it doesn't converge to a specific number. Moving on. Insert one geometric mean between 4 and 64. Alright, so in order to solve geometric means, we'll be using the formula square root of A and B. So when we put this in, 4 times 64 would be 256, and square root of 256 is simply just 16. So 4 64 is 16. As simple as that. It's the basic formula right here in order to solve our 16. For our final question, insert 3 geometric means between 3 and 243. There are actually multiple ways of solving this, but I want you to actually learn this specific method. 3 and 243. So let's just put it right here. 3. Notice that this is an odd sequence. It asks for 3. So we can actually refer to the squared formula. So we do 3 times 243, or 729. The square root of this is simply 27. So its middle value would be 27. And we can do it another time. We could do square root 3 times 27 and plug it into the calculator. We end up with 81, or simply 9. And we can do it again here. 27 times 243 square root. We end up with a large value, 6561. Oops. Square root. If we square that, we end up with 81. So these are our values: 3, 27, and 81. You could actually just simply use the geometric sequence. However, this is fun to say the least. Although it may sometimes be time consuming actually, if there's a lot of unknown variables or blanks, So yeah, that basically concludes our relatively long lesson. I will flash the formulas here once more. Don't forget to really practice, because practice really reinforces, especially in mathematics, your cognitive skills. Thank you again for spending your time, and farewell.